Uh, at the end of the last lecture, we were here that when we were talking about ions, singly charged, doubly charged, but single atoms. Sometimes, but in many cases, there are polyatomic ions. That is a group of atoms that act like one ion. The ammonium ion, NH4, it has +1 charge. Similarly, the carbonate CO3 has -2 charge, and the PO4 it is the phosphate ion which has -3 charge. So they also behave, when it comes to the interatomic bonding, they also behave like single ions, and they can bond. But be careful, when things are bonded together, they keep attain the charge neutrality of the final compound. If the final compound is not neutral charge-wise, then obviously it will not be a stable compound, and whenever it comes in contact with another opposite charge, electron, proton, or element, atom, ion, they will bond together and the state of the system will change. So charge neutrality is must. For example, here it is a sulfate ion, SO4, which has -2 charge, and you are interested in making sodium sulfate. So a single sodium ion will not be able to form this compound, and even if it forms, it will not be a stable compound. For this purpose, the sodium sulfate will be Na2SiO4. So the stoichiometry must be correct in order to achieve simple compound. Whenever in science we say it will happen and it will not happen, this doesn't mean that this thing is not possible. You can do many things in science. I'm not saying any, but many things in science which may not be stable, which may not be neutral, but when science talks of equilibrium or stability, they mean that the thing can independently survive and it is stable. So NaSiO4 can be a compound, but it is not neutral. And the correct stoichiometry is Na2SiO4. So how things happen? A3 Al+3, it is aluminum ion. Aluminum ion. Please note, alumina is Al2O3. Alumina is Al2O3. Aluminum ion is elemental aluminum which has +3 charge. And NO3 nitrate, it is a polyatomic ion which has -1 charge. So it is not possible to form a stable compound by combining Al+3 and one NO3 polyatomic ion. But to satisfy, to neutralize the aluminum +3 charge, you will need 3 polyatomic ions of nitrate to make this compound. Here, Al1 and NO3, 3 times NO3. Al1 and 3 times NO3. So it will be a neutral compound. So the bonding should be also of that type, which we are going to now explore. Properties of ionic compounds, they usually form crystalline structures. Think about it. Crystalline structure means that various planes of the unit cell are at specific angles. They cannot be randomly oriented. If the bond is weaker, then there is chance of random orientation, and when randomness happens, we move from crystalline towards amorphous material. So the main characteristic of ionic compound is they will be mostly crystalline. You can't exclude amorphous material, but I'm using a word mostly. So it doesn't exclude the amorphous materials from this sort of bonding, because there are many glasses which are ionically bonded, but preferentially they will form crystalline structure if they are given a chance. And what about this chance? Let us explore this chance. What is this chance? The chance is basically the free energy of the final system. If the free energy of the compound formed as a result of ionic bonds is higher than the amorphous counterpart, then the material will tend to become amorphous. So the final free energy of the compound also decides which type of structure will form. Also, certain materials will tend to form crystalline materials. They will be prone towards crystallization, but it is the process you use. For example, you make a melt of ions which are bond ionically upon cooling. Now, if you allow all the ions at their own wish to go to the desired ions and form bonds, then they will go. The natural choice will be to form the bonds with the minimum free energy. But if you stop them or you freeze the structure as a melt, freeze mean that they were running towards one another, but you stop them in the middle. So what does stopping mean in the material science? The stopping means that the material wanted to cool down, the melt wanted to cool down in a proper sequence, but you didn't allow it to do that, and you suddenly squeezed or freezed the system wherever the ions were. You froze them there. In that case, you arrested the randomness of the material. It wanted to form a crystalline compound, but you kept it random artificially. You kept it amorphous artificially. So when people say that this will happen, they mean that theoretically, when equilibrium phases are formed, this will happen. If you interrupt in the middle, you make quicker cooling and don't allow the ions to reach the minimum free energy positions, then you will not be able to see that. So equilibrium is always the focus of science, or material science is always on equilibrium phases. This page, if I ask somebody to fold it so that it occupies the minimum space, so the person will fold it in this manner, like this. And in this way, it will have, just visualizes like the unit cells are the planes within a crystal. So every plane will go at a proper place and the minimum space will be covered. visualize this space as energy. Now it wanted to occupy the minimum space, but what I did, I froze in whatever position the ions were. So I kept it random. And whenever this these ions find an opportunity, they will try to go to the minimum possible energy states. It is just like that you are standing on the top of the floor. So the top of the floor, the roof, is not your minimum energy position. The minimum energy position will be on earth, on the ground, but the roof is keeping you there. And whenever you reach the end, you will come down. The same thing is here, that in the solids, you freeze the ions at random positions. And whenever you heat the material, again the ions will move when they are free mechanically from the hold, from the force of the structure. The first thing they will do, the positive will go towards negative and the negative will go towards positive. Then, if this was one atom and this is another atom, it has all the choices to bond here, 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 and anywhere around that. But the atom will prefer, if it has a choice, they will form a bond at an angle where the energy is minimized. And the minimum energy will give you the more stable and equilibrium structure or equilibrium phase. So this is the actual thing, that why the there are rigid angles, rigid positions of atoms, and bond angles, specific angles there. So all these come from there. A regular repeating arrangement of ion in the solid is the crystalline structure. You know, ions are strongly bonded. Strongly bonded means at definite angles, and it is difficult to move them, and the structure is rigid. High melting points because of strong forces between ions. As a scientist, as a material scientist, you must realize you shouldn't say that heating something melts. It is news. If you say that when something is heated and it melts, anybody can watch it and can say that. No. What is melting scientifically? Scientifically, melting is the breaking of bonds. So, if it is easy to break the bonds in a solid, its melting point will be lower. And if the bonds are stronger and it is difficult to break those bonds, then this means the melting will need higher temperature. And when they need higher temperature, this means the material will have higher melting points. So the common properties, the general properties of ionic compounds are they will prefer to form crystalline structures. And you know the crystalline structure is regular repeating arrangement of ions in the solid. And I had told you that it must have the compulsory condition for crystallinity is translational symmetry. Ions are strongly bonded. Strongly bonded means the structures are rigid, and the strongly bonded means the melting points are high. So instead of memorizing these things, physically and visually visualize the actual situation. So you will not need to memorize things, but you will understand things, that why this property is coming in a specific material. And my aim as a teacher is to induce this in your mind, that such lessons, if it is physics, if it is material science, they are not learned for something else but for application. And when you know that this sort of bond is needed, then as I told you, that you will need which form of material will form which type of bonds. And when you know that, that then you will know whether the bonds will be stronger or the bonds will be weaker. When you know about the weakness or strength of the bonds, then you will know about the melting points of the material. So if you are using or making a material, engineering a material for a specific application, for example, you are making a furnace tile, then its melting temperature of the furnace tile must be much higher than what you are melting in the furnace. If you don't know that, you can't be a material engineer, in simple words. So whatever you do, think first logically and scientifically, then you will be able to move forward. Crystalline structure, the positive cations stick to the negative anions like a magnet, is shown in this figure. So this is solid structure. Obviously, there will be angles, perfect angles, precise angles, and the negative and positive you know. Do they conduct? Now, when you are thinking of bonds and one ion had one electron surplus, and that was taken by the other ion, and that ion had one ion deficiency. One had one surplus or loosely bound electron, and the other needed that electron. So the loosely bound electron went from one ion to another, and it was consumed there, adjusted there. So there is no free electron there. When no free electron is there, then how is it possible to conduct electricity? Because conduction is the moment of electron. So when you think of conduction, think of don't think of the electrical wiring, but think about the atomic structure, the type of bonding inside the material, that whether it will be a conducting material or not. Conducting electricity is allowing charges to move. In a solid, the ions are locked in place because of bonds, as I told you. Then ionic solids are insulators because there are no electrons to be easily moved around to conduct electricity. So they are insulators. They don't conduct electricity. When melted, the ions can move around. So at low temperatures or at room temperatures or at temperature at which the electrons cannot move, the charges cannot move, the material will be insulated. But when melted and the temperature is raised, melting ionic compounds conduct electricity because you give the opportunity to the ions to move around, and electricity is nothing but the moment of charge. So at different temperatures, the behavior, the properties of the materials change because of the electronic and electromagnetic changes in the electronic or electromagnetic structure of the material. First get them to 800, then check, and you will see that the material which was insulator is now conductor. So whenever you use a material for a specific application, then keep that in mind, that at which temperature are you using it, in which environment you will be using it. A material will be an excellent material for a specific application, but when it is heated up, it may not be left there like that. If it is made wet, if it is exposed to rain, it may not work like that. So as an material engineer, you must take care of all the various options, that what will be happening to this material, and is the material suitable for that specific application. When insulators are dissolved, in water. They conduct electricity because again, there is possibility of movement of charges. Ionic solids are brittle. This is the most important point I want to tell you, that why ionic solids are brittle. Here, I show you two structures. It is one structure basically. These are positive and negative ions. They are bonded together, and there are no free electrons around. So if I move this plane over this plane, what will happen? I will bring this positive charge over this positive charge. I will bring this negative charge over this negative charge. I will bring this positive charge over this positive charge. And since there are no free electrons or any electron in the surrounding, the bond cannot be retained, but the electrostatic repulsion will push these is shown here, and the material will break down. So ionic solids, if I have an ionic solid, for example, piece of stone, and I try to bend it, it will break because it is ionic solid. In comparison to this, if I have a metal, for example, this key, and I try to bend it, it will bend because of the burning which is coming in the coming slides. Covalent bonds. In ionic bonds, please note there was a complete transfer of electron from one ion to another. This is a chemical bond again that forms between non-metal atoms via sharing of electrons is called a covalent bond. In the ionic bonds, we say that they form between metals and non-metals. But here, the non-metals within themselves don't have that much availability of electrons to be transferred, and they share electron. And when the electrons are shared, the resulting bonds are covalent bonds. For small electronegativity difference, atoms are unlikely to lose or gain electron. This is very important point to understand, that if this atom and this atom have large electronegativity difference, then the thirsty one will take the whole glass from this one and drink it. But if both are not that much thirsty, the thirst is equivalent, then the glass will hang in between the two. The glass will remain suspended between the two. The same thing is here too, that non-metals and metals have large electronegativity differences, and because of that, complete transfer of electrons occurs. But if a bond forms between a non-metal and a non-metal, there is not that much electronegativity difference to completely take electron from one to the other, and that will lead to the sharing of electrons between the two. The stability demands transfer, but the number of electrons in their outer levels make this difficult. And the only alternative left with them is sharing of electrons. For example, in hydrogen, each hydrogen has one s1 configuration, electronic configuration. Here, this is hydrogen molecule, and each hydrogen has +1 charge. Two possibilities are there: the spin parallel, not allowed by the Pauli exclusion principle, and repulsive, are anti-parallel spin, lower energy and attractive. Please follow this. Pauli exclusion principle says no two electrons can occupy the same quantum state. Here you have the same quantum state, 1s orbit or shell, and you have two electrons. So the only possibility is that both the electrons can be in the same s orbital but with opposite spins, and quantum mechanically when you calculate the energy, their energy will be lower because of attraction and no repulsion, and electrons will share a bonding state with lower E. So the bond will be like this, like this. The orbits, and they will be shared, they will come into the same orbit, and the two hydrogen atom will make a hydrogen molecule by means of covalent bond. Covalent bonds are directional, again, because the angles are there, directions are there, located along the line between the atomic nuclei. Attraction to attain inner gas configuration is, in the ionic case, the transfer was used, the transfer of electron was used to attain inert gas configuration. Here, the sharing of electron is used to attain the inert gas configuration. Repulsion between electrons with opposite spins. Here is also an equilibrium distance between atomic cores, which is called the covalent radius of atom. When you bring the two atoms together, and when the orbits start to mix up, and there the electrons don't find different quantum state in the same shell, then they start to repel. They increase the energy. The energy is not going down. When the energy is going down, attraction occurs. But when the energy is going up, repulsion will occur to minimize the energy. And that is why they have a covalent radius. You can't go beyond that point. Another factor stabilizing covalent bond is the indistinguishable nature of electrons. For example, if the electron of atom A if the electron of atom A and the electron of atom B are there, then if they are shown like this, that the second electron comes to the A and the first electron goes to the B shell, for example, electron 1, electron 2 have the same energy in both states, and the molecule will resonate between them. So the indistinguishability between the electron leads to resonance. This resonance lowers the energy of the system of interacting particle and therefore accounts for covalent bond. If that resonance is not there, then there will be no bond because the energy will go up, and that What should I tell you to explain this? I am moving these two fingers in front of you, and you sometimes feel that they are not two fingers but three. This third one is coming because of that resonance, and both the atom feel that they are in that resonant state, and that keeps them bonded together. So it is just a visualization that this finger and this finger both feel here to be bonded with that resonant state. The covalent bond share electrons are attracted to the nuclei of both atoms. So both the nuclei of the atom A and B, or the atom 1 or 2, are attracting that couple of electrons, and they move back and forth between the outer energy levels of each atom in the covalent bond. So each atom has a stable outer energy level for some of the time. Here again, the question of time, the point of time came, that these were two orbits, they shared the electrons, and it became almost shared orbit between the both of them, because the nuclei are in on their places. They are not shared in the bond. The orbits are shared. So when the electrons, both the electrons comes here in the middle here, this nucleus and this nucleus both attract them towards them, and that is the bonding, the reason for the established bond. The neutral particle formed when atoms share electron is called a molecule. A molecule is the basic unit of a molecular compound, and atom is the basic unit of an atomic compound. You can see how molecules form by sharing electrons in this orbit. Now, as I told you, that I will show you that this is one electron around this nucleus of hydrogen atom ion, and this electron is with this. But when they are bonded, this means that neither this nucleus has lost the electron nor this nucleus has lost the electron, but they came into such position that this nucleus considers the electrons to be with it, and this nucleus considers the electrons to be with it, and both are attracting this pair, a couple of electrons, and this is the reason for bonding along the line joining the centers of two nuclei.